Ladies and gentlemen, today I wanted to talk about oscillations. This is a important topic because lots of things oscillate. They go back and forth. They cycle through series. I've got two examples here primarily that I want you to think about. The first one would be a spring that has a mass on it, and that mass is going up and down because the spring pulls it up and gravity pulls it down. Those just go back and forth. The second one over there on the right would be a simple pendulum, we call that, just a ball or some kind of mass on a string, and it's swinging back and forth. Here again, it's got, we set it away from the center line, so it's got some potential energy. The potential energy turns into kinetic energy. The momentum carries it on over to the opposite side, and then it goes back. And again, gravity is working to pull it back toward the middle. And so in both of these cases, you have an object that's going through motion over and over and over. It's that same cycle. That's what we're talking about here with simple harmonic oscillation. We could graph this, and it would look something like this, where we have a function that goes up and down. This is a sine wave here. That might be a good option. Cosine might be a good option too. You might remember that sine starts at 0 and goes up through one complete cycle every 2 pi radians, whereas cosine would start here at 1 and go down and back up. So if it's something where we're, say, lifting a mass on a spring and then dropping it, letting it go, and it starts at the top and goes down, might make more sense to use cosine. Whatever. They're both kind of the same thing, and with a phase shift you could treat it either way. But I've got some definitions here I want you to think about. T, capital T there, is the period. How long does it take that mass to start at the top, go all the way to the bottom, and all the way back to the top? One complete cycle there. How long does it take the pendulum to swing from the right all the way to the left and all the way back to the right again? That's the period, that amount of time in seconds. The frequency is the number of cycles per second. So, if it takes 2 seconds for that thing to swing all the way over and back, then every half second you're getting, you'd have a frequency 1 over t there, you can see. And that's an important formula that you should write down there. The frequency is the inverse of the period. And so you can always work that out. The unit on that typically is hertz, named after Heinrich Hertz, a guy that worked on radio and a whole bunch of stuff. But it's basically cycles per second. All right, there's one more thing here. We got the period, the amount of time, the frequency, how many cycles every second this thing goes through, and then lastly the wavelength. The wavelength would measure the physical distance in meters of one complete wave. So if we started right there at the origin, went all the way up, all the way down, and back, there is a physical distance that wave occupies. If you went down to the beach and you took somehow could freeze all the waves where they are, and you stretched a tape measure from the top of one wave to the top of the next wave, that would be the wavelength. Or you could do like we did here. You could start at the middle, go all the way up, all the way back down, and all the way to where you started, and you're ready for the next cycle to begin here, the next wave. So that distance is the wavelength. I mentioned briefly that gravity plays a role in both of those, both the bouncing spring and the pendulum, that gravity tries to pull it back to its beginning place. And so that's what we refer to as a restoring force. And I don't know that you need to know a whole lot about that. You have seen this before. Hooke's law here, the force that the spring puts on the mass would be equal to negative kx. K was a spring constant telling us how strong that spring was. X is the distance that it's displaced. A similar thing happens here in the case of pendulums and gravity, mg, and all that. But that's an example of a restoring force where that spring pushes and then gravity pulls it the other way, and eventually we're going to set those equal and do do some stuff with it. But for right now, whenever I say restoring force, it simply means the spring tries to push back to where it started. The pendulum tries to swing back to the middle. So that. All right. We were talking about the wave and modeling that wave in mathematics. And I said that a sine wave would work, a cosine wave would work. Here we're using cosine simply because we're picturing something that starts at its highest peak and goes all the way down and back to where it started. So that would be one wave. If you measure this physical distance, that would be the wavelength. If you measure the time it takes to go from here to there, that's the period. And if you measure how many times it does this, one complete cycle, how many times it does that per second, that would be the frequency. So we've got all those numbers, and keeping up with those is a pretty good trick. I've got some tips down here. The frequency is the inverse of the period. We're going to have another one here called the angular frequency, which is 2 pi over t. 2 pi would be one cycle, right? Whenever you see 2 pi, you need to be thinking in radians. Your calculator needs to be set to radians. So you might want to go ahead and switch that over. But here's 2 pi. It makes one cycle. How many seconds does it take to do that? See how it's a radian per second thing? And that's like what we did with angular velocity back in Physics 1. So 2 pi f, or 2 pi over t, that f again is 1 over t, so I picked this up and substituted it in for f, and I get this. These things kind of jump back and forth, but right here is that model. A is called the amplitude. What's the highest point that wave reaches up there? So it goes up to positive A, back to 0, down to negative A, 0, and it just keeps doing that motion right there. If I replace that 2 pi over t with omega, then I just get a cosine omega t. Okay? Basically, they're going to give you those numbers, you plug them in. And what it's asking is, where is this object going to be as a function of time? So I pull the mass up here, I turn loose of it, that starts the time, and if you hit go and count off 3.4 seconds, then all you'd have to do is put the 3.4 in here. You'd have to know some stuff about how strong the spring is and all that. You'd have to know what the amplitude is, but basically you're going to take your calculator and multiply a number times the cosine of some number times some other number. And there's not a whole lot to worry about there. This is a mass that's bouncing, that's oscillating up and down. It also works if the mass is bouncing like on a table. Let's say we secure a spring here on the edge and this mass, and we could pull it some distance away from the starting point, or we could push it here to negative A and turn loose. The graph down here, they pulled it out to positive A, stretch that spring. When they turn loose of it, that starts the time. Spring's going to pull back this way. That compresses the spring, which pushes it that way, which it's just going to bounce back and forth right there. So again, same math model, a cosine omega t. You got the same reminders there, everything. This thing works side to side. It works up and down, whichever way you want to go at it. Now, since we've got the position of this thing, x equals a cosine omega t, it would also be nice to know the velocity and the acceleration. Some of you have had calculus, and if you have, then you know that the velocity is the derivative of x with respect to t. When I take the derivative of this up here, a cosine omega t, then I'm going to get a sine omega t. Cosine becomes sine, and I've got to chain rule it. I got to get that omega and pull that out right there. So that would be the velocity at any point in time of that mass on the spring. If you have not had any calculus, don't worry about any of this stuff in the middle. You just need to know that the velocity equals a omega sine of omega t. All right. For finding the acceleration, you're going to do exactly the same thing. Take the derivative again, or just write down a as a function of time, is equal to negative a omega squared cosine omega t. Those of you that have had calculus know that when you take the derivative of sine, you get negative cosine. And of course, you got to reach in here and grab the constant and bring it out so you get that omega squared there. All right. One last thing here. That last line shows us the force on the object. You know that force is equal to mass times acceleration. Well, I've got the acceleration over here. So if I simply take that and multiply by m, now I have a function for the force. So you see how these four tell you just about everything you'd want to know about that object on a spring. I know at any point in time where it is, how fast it's moving, what its acceleration is, and what the force on it is going to be. And it's all a matter of plugging in some numbers here. We're going to do one of these in just a second. But let me show you one more thing before we do that. Right here, sometimes they'll say, go find me the maximum X or the maximum V, maximum A, maximum force. And that's a simple matter. All you got to do is cross off the trig functions. Why is that? Well, if I'm looking for the biggest thing that I can get out of X, the maximum X, then I know that this cosine bounces, oscillates between 1 and negative 1. So if I just cross it off and put a 1 right there, then the maximum displacement from the center line there is just going to be X equals A. The velocity is going to be A omega. The maximum acceleration would be negative A omega squared. And the maximum force on there would be negative ma omega squared. And again, just putting a 1 for all those trig functions, just strike them out. No big deal. Okay. There's one other factor that I'd like to put in here before I do this little example problem for you. But here's our cosine wave right there. And it starts at the top and goes down and back. There's every 2 pi. Here's one of those. There's the second wave. I got a third one over here before the origin starts. But it's very possible to phase shift this thing, to move it left or right on the thing. So what we could do, this is cosine of some angle, but here cosine of some angle plus some phase shift angle phi right there. So normally it would start here. When I add an angle, it actually shifts the starting point of this, if you will. You know, if I start at 0 here, well, cosine of 0 is 1. So I've still got that same 0 right here, but now my phase angle is pi over 2 or something, right? So it's going to shift that line away from where it was. Now it's like I'm taking the cosine of pi over 2 when theta is 0, even though, you know, that would normally be 1. Now I'm at a different place on the axis, on the x-axis, so it slides that whole thing left or right. All right, here's that problem that I was promising you to take right here. I've got this up on my other board, so I'm going to slip over here for a second, and we'll read through this. A 2 kilogram block, that's the mass right there of that object on the spring, sits on a frictionless surface. We don't have to worry about friction here or anything, attached to a fixed spring. Fixed meaning it's anchored to the wall. The block is displaced by 5 centimeters and released. The period of motion is 1.57 seconds. Okay, so the trick to doing this, of course, is to learn how to read these things. It's just like kinematics, just like everything else that we've done. 2 kilograms is obviously the mass. Right here, x is 5 centimeters. But notice that that's the distance. It starts here, and I'm going to pull it away 5 centimeters. So, yes, it's x, but that a is what we're really after right there. So let me just make a little list here of variables. M equals 2 kilograms, and that a, that amplitude, that farthest distance away from where, from that center line is 5 centimeters. There may be times when you'd want to go with meters instead of centimeters, so just kind of be aware that's an option. I'll probably leave this one in centimeters, but whatever. Next numbers is 1.57 seconds. They're kind enough to tell us that that's the period. So t equals 1.57 seconds. And here's what they want. They want us to find 1, 2, 3, 4 things as functions of time, putting in this 1.57 seconds for our thing. All right. So that's the trick on this right here. So we get busy. We say, okay, x. I've got a function for x. I even put it down here so you could see it. I know that my x at any point in time is going to be a cosine omega t. And I go, this is great. I got an a and I got t and omega. Uh-oh, I don't have omega, right? So this is one of those things that ties into some of those other things. You need to have this thing right here. Remember I said these were good to write down. Omega is 2 pi over t, or it's equal to 2 pi f. So coupled with that right there, then we've got what we need. Omega equals 2 pi over t. Since I have the period here, I'd probably use that one. If they'd given me the frequency, I'd go over here. But I'm going to write that down on the thing as well. Omega equals 2 pi over t, and I can work out what that is. My t was 1.57 seconds, and maybe I want to get a number here, or maybe I just want to put that in to the function. Let's just get a value here for this thing and be done with it. If I take 2 pi and divide that by 1.57, there is 4.002. I'm going to just call that 4 in the interest of sanity here. So let's put down a 4 there. That again, remember this is measuring radians, and that's in seconds. So I'm going to put the units on there as well. All right, we're ready to put this in now. Here is my 5 centimeters times the cosine of 4 radians per second times the time was 1.57 seconds. And you notice here that the seconds on top should cancel the seconds on the bottom and have nothing but radians. When I take a trig function, I need to have an angle, nothing but an angle in there. And in this case, that should be measured in radians. So make sure that everything cancels out there. And then you're ready to plug some numbers in and see what happens. I could just come along and say 5 cosine 4 times 1.57. And I get 4.99. It's almost up there at the top. I'll put 4.99 just to show that it's a little bit different. But if I had used a different time, you know, like 5 cosine, here's my angular frequency right there. A little bit later on, let's say at 1.7 seconds. See how it's on its way back down? And whatever time I plug in there, I'm going to get a different number. And see there, it's actually down below. So somewhere in between, when I use 1.5 seconds, it's almost here. And then a little bit later on, it's here. And then a good bit later on, it's actually way over here somewhere. So it's, you know, it's on that path going back and forth, and the time matters because it's going to, it's constantly changing its position. And this is how you would find it. We'd like to know the velocity right there, a omega sine omega t. You know, you're just plugging numbers in. So it looks like that. I like to put the parentheses around it just to remind myself to take the sine of all of that. But my amplitude again was 5 centimeters. Oh, you know what I should have done? I should have put a unit on this. Since we were doing 5 centimeters, I'm at 4.99 centimeters. Okay, now watch this one right here. When I take the 5 centimeters, here's my omega, which is 4 radians per second, times the sine of omega, which was 4 radians per second, times my time, 1.57 seconds. Again, the seconds cancel out, nothing but radians in there. And I can push all these buttons, and get my, I'm going to clear this out. Oh, let me emphasize here too, let me make sure too, when I hit my mode button here, see how my calculator's in radians, and anytime you see that omega or 2 pi, you need to be set to radians there. All right, so we're okay. 5 times 4 times the sine of 4 times 1.57. And once we've got those numbers figured out and marked down for what they are, then there's really nothing too scary about doing this. We said these seconds cancel out, so I've got radians. I take the sine of radians, I just get a number. Over here, centimeters times radians per second. Remember how the radians kind of run off and hide. I don't really want to mark that out, but I certainly have centimeters on top, seconds on the bottom. That looks nice because I was looking for a velocity. We could measure velocity in centimeters per second. If you wanted to change it to meters per second, move the decimal place over 2 more times, right? That negative right there is a directional thing. It tells us which way it's moving. And hopefully that makes sense because we said at 1.57 seconds it was going to be here. At 4.99, not quite. This was 5 centimeters, so we're, here. Could be moving to the right, could be moving to the left. As soon as we see that negative sign right there, we know it's moving this way to the left. And that's further fortified by the fact that, remember, we did a couple more of these, and I think it was like here, and then the 2.2 seconds was right there and stuff. So it's on its way back right there. But this is a pretty small number, right? Why is that such a small number? Well, because it's out at the edge, and what's it do at the edge? It goes all the way to the edge, and it stops, slows down getting out there. Then it's going to speed up coming back this way. It's going to hit the maximum speed right here. And the velocities at the ends are going to be 0. Okay? Something like that. All right, real quick here. The acceleration is negative a omega squared cosine omega t. And we get busy and we run the numbers again. I think you can see there's nothing too bad about this once you get the hang of it. Looks like that. You put your cosine 4 radians per second times 1.57 seconds. What is the acceleration on that mass? How fast is it speeding up? Plug in the numbers, find out. I got 5 times 4 squared times the cosine of 4 times 1.57. And that's a 79.9. I'm going to just put 80 centimeters per second. Not second. What is it? There's a second which got squared. It's actually centimeters right here. And second squared. Like that, of course, everything over here is just goes away. So that's our answer there. Like that. And I left out that negative sign right there, didn't I? So that's important because we know this thing is moving to the left and it's accelerating to the left. And so that negative sign says to the left right there. So don't forget that. Lastly here, if I want the force, that's a simple matter. Just take mass times the acceleration. I'm going to just use the number right here and plug it in. I could put all of this again like the formula says here, but I already have the acceleration, so why trouble myself? There's a 2 up there. So 2 times negative 80 would be negative 160. When I do kilograms times meter per second squared, that's going to give me newtons of force, and that's my force at 1.57 seconds. So that's all we're doing there. You're using those trig functions, that sine and cosine, to kind of model what that thing's doing. You do have to know these little workarounds, little substitutions to get all the numbers and stuff, but you can do this. It's not too bad. Let's find where we were. I think it was that one. Okay. We talked about the phase shift. Okay, there we were. All right. You got this other thing called the period, which we've talked about. We know that that's the time that it takes to go through one full cycle. But right here, I'd like to work out how to find that period from first principles here. And I'm going to kind of gloss over this thing. It's got some calculus in the middle, a differential equation specifically, and I'm not so much interested in doing that and you being able to do that, but just to kind of see where this gets set up right here. Let's see what happens. We know that F equals ma, and that the force that's driving a mass on a spring is kx, and specifically negative kx because the force is in the opposite direction of the displacement. Well, a is the second derivative of x. If you're in first semester physics, don't worry about that. I mean, if you're in the algebra-based physics, don't worry about all this mess in the middle here. We're going to get to a box at the bottom that you want. But that's equal to negative kx, as it was up here. I fill in right there for a, and I've got it over here for x. And notice that cosine omega t is going to cancel cosine omega t, and the a cancels the a, so I end up with negative m omega squared equals negative k. All right. I could solve this thing for omega. I'd have to divide both sides by negative m. The negatives would cancel. I'd have k over m. That would be omega squared, so I'd want to take the square root of both sides, and then you know what, we wouldn't even have to do that with a differential equation. We could just make the substitutions that we had, so I misspoke there. You could do it that way, but this isn't differential equation class. Cosine would be a really good option there because we're looking for something we can take the derivative of and get that same function over here if you've had that. If you haven't, don't worry about it. All right, just put in the substitutions. Strike that line right there. All right, we were talking about omega. I'd have to take the square root to get rid of that right there. So omega is the square root of k over m. All right, I know that omega is 2 pi f. So I could change that around and say, well, f would be 1 over 2 pi square root k over m. And what I really want is the period, which is the inverse of f. So I got to turn this whole thing upside down on its head. 1 over 2 pi is just going to, when I invert it, it's going to become 2 pi, and I invert square root k over m. I get the square root of m over k. So this last box here is really the best of all of these, the one that we want. That is capital T, the period that we're looking for. So just kind of going back here, and we'll do one of these real quick as soon as I can make some room. If I had a mass of I don't know, 1.3 kilogram mass on a spring with k equals, I'm going to pick a number here. I don't know if it would be a good number or not, but let's say 4 newtons per meter. That might be a good spring constant for this. Then what we are looking at is this horizontal spring, and of course we didn't put in friction here, so we're not playing with friction here. But I've got a horizontal spring with a mass on it like that. I know the mass, I know the k, the strength of that spring right there. To find the period, I say T equals 2 pi square root m over k. So that's a simple matter to work out right there. My mass was 1.3 kilograms, and my k value on the bottom is 4 newtons per meter. And I can grab my calculator real quick and say 2 pi square root 1.3 divided by 4, which would be 3.58 seconds. If you'd like to see that turn into seconds, which you certainly should, don't take my word for anything here, up underneath that radical right there, I've got the square root of kilograms on top and newtons per meter on the bottom. So I've got a compound fraction here. First thing I'd probably do is invert and multiply that meter up top. Here's a Newton like that. And then I would remind myself that a Newton is really a kilogram meter per second squared. And let's just invert this and see what it'll cancel out. I've already got a kilogram and a meter on top. I want to invert this thing, so I get second squared on top and a kilogram meter on the bottom. The kilogram meter on the top cancels the one on the bottom, same for the meters. I've got the square root of second squared, which would just be seconds. All right, and that's how you get to the unit there. But 3.58 seconds. You take this mass and this spring, and you pull this thing away from the center line there and turn loose. It's going to bounce back and forth between these 2 points, A and negative A. Every 3.58 seconds. It's going to start here. It's going to go all the way there and all the way back. That's the harmonic motion there. Simple oscillation. It's going to take 3.58 seconds to make that trip. There and back. All right. Almost done here. Oh, I guess that was actually an example that we did, so we don't need to do this. If you wanted omega and f, you could either run it through the formulas here, or you could take and you say, well, shoot, man, I know that omega is 2 pi f, and I know that omega is 2 pi over t. And since I've got t, I could plug it in here and solve for omega. Or then I could, say, well, 1 over t is f. So as soon as I've got that f, I could plug that in here and get omega. But you're not usually looking for omega. It's usually that period that's the most handy of those. Here's another derivation right here. Mass on a spring ends up the same thing. And, so I won't go through that again, but this is a hanging one there, and where gravity's involved. Let's skip over that one. Here's the energy that's stored in a spring. So just before we do this, let me get you to think about this right here. When I grab a hold of this mass and I stretch it away over here to A, then I've displaced it. And we say that it has some potential energy. We saw in first semester physics that was equal to 1/2 kx squared. All right. If I just stretch it over there and don't release it, that's how much energy it's going to have. When I turn loose of it, it's going to come back over here, on its way back over here and back and forth. So it's going to have kinetic energy, which would be equal to 1/2 mv squared. If you combine those two, this expression will give you the total energy at every point on the thing. So if you knew its position and its velocity, then you could find the total energy. Or once you knew the total energy from this or this, then if you knew the position, you could find the velocity. Or if I knew the velocity, I could get the position, something like that. All right. I've got a couple more of these expressions to find the period. So right here is the simple pendulum. How do we find the time it takes to make one complete cycle there? Well, you start off and you say the torque is equal to RF. This thing is going to have some kind of moment of inertia, and when I pull it away, then gravity is going to try to pull that back, right? And it's working on the center of mass, and since all the mass is here at the bottom, then gravity is pulling straight down, but it's trying to restore it. That's that restoring force again. So I got to think about the torque on this whole arm here, but it really acts right there. And that's equal to the moment of inertia times the angular acceleration. So I've got R is the distance from the pivot point to the center of mass. That's just L, the length of my string. The force on it is going to be mg sine theta, where because this is pulling straight down, and there's that angle, when I pull it away from you know, the perpendicular line, then the gravity pulls straight down. So I got that sine theta goes in there to give me this component. We make a little assumption here. We say, well, theta equals sine theta, or is very close to, it's almost equal to, for small angles. We're not talking about pulling this thing way up here, you know, 80 degrees off and letting it go. These are small angles that we're talking about here. So if theta equals sine theta, then I can make that little substitution, just take that sine theta, replace it with a theta right there, and then right here, you know, I've got that second derivative again. Don't worry about that if you haven't seen it, but it ends up right there. That one is a differential equation, and you would know, you guys don't need to know how to solve that, but in order to get the solution, then you come right here and you say t equals 2 pi L over G. All right? Forget about all this stuff, okay? This is the period that we're looking for right there, 2 pi L over G. So if we had a situation where we knew the length of a pendulum, that's really all that we need to do. You know that they used to make clocks, grandfather clocks, that would keep time. And the whole thing worked by this pendulum swinging back and forth. And so the question becomes, how long does that string need to be? Well, what if I want it to tick once a second or something? T equals 2 pi L over G, and this is all under square root right there. So, you know, right here, maybe we need to say find L for T equals 1 second, something like that. So I'd get busy and I'd solve this thing for L. It's under the radical here, so the first thing I would do is square both sides. T squared equals 4 pi squared. Remember, if I square the entire side, then everything, 2 gets squared, becomes 4, pi gets squared, there's pi squared. When I take this, when I square the square root, those are going to cancel, so now I've just got L over G, and I move all this stuff over to the other side. I'm going to multiply both sides by G, so I get T squared over G, and divide by that 4 pi squared. And there's my L right there. How long does your clock pendulum need to be? I want the period to be 1 second. If I'm using the clock here on Earth, then I'd have 9.8 meters per second squared. Here's a 4 pi squared on the bottom. And so you could find out pretty quickly how long that needs to be. I'm going to say divided by 4 divided by pi squared. I've got two things in the denominator. Make sure you divide by both of them. 0.248 meters would be your number there. That's a decent length. About 25 centimeters. Okay. About as long as your forearm, maybe. Something like that. If you had it twice as long, you know, that's going to change the period. The longer you stretch this thing, then the more time it's going to take to go back and forth. So that's handy. All right. I've got this other kind of pendulum that's called a physical pendulum. It's not a ball where all the mass is at the bottom of the string. It's any weird shape that you have at all. Okay. You could take a sheet of plywood and you could cut this weird blue hourglass shape out, whatever that is, and you could drive a nail through it right there, drill a hole, drive a nail into the wall, and this thing would swing back and forth around that nail, and the period, the amount of time that it would take, is given by that expression right there. All right, you'd have to know I being the moment of inertia of this whole thing. That makes sense since it's going to rotate. How hard is it to rotate, right? That's what I does for us. I'd need to know the mass of the whole thing. I'd have to know L, the length, the distance from the nail to the center of mass right there. All right. So, you know, just to, I don't know, one of those maybe, T equals 2 pi square root I over MGL. Okay. You just put the numbers in, whatever they are. Let's say the moment of inertia is 4 Newton meters squared, and the mass is 3 kilograms. G, we're here on Earth, and the distance from the pivot point, you know, whatever this crazy thing looks like, there's the nail, and you're coming down here, this whole thing centers up right there, and that distance L is, I don't know, 2.2 meters, right? And you just come over here and you plug the numbers in. Push the button, see what you get. All right. So it's a plug and chug. You're just putting those numbers in. All right. One more here. This is the torsional pendulum. Basically, on this one, you've got something kind of stiff here. It might be a metal rod or something. Then there's this object hanging here from it. But if I were to take that object and rotate it just a little bit and then turn loose, the torsion, the twistingness of this rod right here is going to flex it back one way and then the other. It's going to oscillate. This disc right here is going to turn one way and then the other, back and forth like that. My brother and I used to have a tire swing in the yard. So you could think about a tire swing here, and we'd put, you know, each other in it, and then we'd wind it up and up and up and up, and that rope right there would get all that tension, that torsional twist in it. And so when you turn loose of the tire swing, it would swing way around this way, and then you come to a stop and you go back all the way the other way. How long? What's the period it takes to do that whole thing? 2 pi square root I. I is the moment of inertia, and there it matters about the mass of the kid in it. And K would be the torsional coefficient of, what do they call that? The coefficient of torsional stiffness or something. I don't know. But it's a number that says how hard is it to twist that rod there, right there in the middle. So you can see how they're going to give you I, they're going to give you K, you multiply, and you get the period of the whole thing there. All right. This is the last slide, I promise. But there is a thing called damped oscillation. The shock absorbers in your car do this. So, like if you went over a speed bump, you know how your car bounces that first time, but the second bounce is a lot less dramatic, and third bounce you probably don't even notice it anymore, right? It absorbs all of that shock and that bounciness to it. And that's easy to model. All you have to do right here is say, well, if I just put in a exponential decay function on top of that cosine function, then I've got that. So here's the regular trig function that we're using to model that cosine behavior. If I multiply that by an exponential decay, then I get this curve where it starts out at the top, and it's going through the cycle in the same amount of time that it always did, but the amplitude is getting smaller each cycle. Right here is a mass on a spring. It's stuck down in a vat of oil or some kind of thick viscous goo, and if I pull this thing down and turn loose, it's going to bounce, but some of that energy is going to go into the oil, so it's losing its speed there, and it's going to go through this kind of thing. Mathematically, there's my original amplitude, A naught. Over here is the cosine omega t plus phi, whatever you're using to model your cosine. But right here in the middle, they've got that e to the negative, some factors there. All right, and the factors would be involved, would be that this stickiness of the oil, the viscosity. You see this eta right there. Okay, I don't know that I need you to do one of these, but it's kind of interesting to think about how you can slow things down and stop a simple harmonic oscillator too. All right, so very good. That's our first little section. Hope that made sense. If it didn't, bring any questions with you to recitation, and get busy on the lop, and we'll see what happens. Thanks, and have a great day.